Welcome back, Physics Pirates. I hope you had a great weekend. Today we're going to talk about conservation of energy and power as promised. You can see I really dressed up for the occasion today, so you can bear with me and we'll get this lesson done on conservation of energy first. If you'll open the PowerPoint on my website, we'll do section 5.5, conservation of energy. The first two statements in that PowerPoint state this, that we observe that once all forms of energy are accounted for, the total energy of an isolated system does not change. This is the law of conservation of energy. Basically, that says this. You've heard it said that the energy can neither be created nor destroyed, but it can be transformed from one form to another, or transferred, or converted from one form to another, or however you want to say that. Energy is converted. That if you have a system or a system of objects, that the total energy in that system remains constant. Now, can kinetic energy in an engine be converted into let's say other forms of kinetic energy that drive something else? Could potential energy in a system be converted into kinetic energy? Absolutely so. But you're never gonna lose energy, and you're never gonna gain more energy than you put into it. Now, that doesn't mean that you're going to get all the energy out of an engine that you put into it, because we'll talk about in just a minute, there are forces that are known as conservative forces and those that are known as non-conservative forces. So the non-conservative forces actually take mechanical energy away from a system. It may convert it into things like heat or sound, or things that don't help your system. For example, in a car, cars are very inefficient at what they do. They're not very good at converting chemical energy that's in gasoline to mechanical energy to help the car move. They're not good at that. A lot of that energy that's in gasoline is lost to the environment in the form of heat, sound, and other forms of non-conservative energy, or as a result of non-conservative forces, they're not converted into mechanical energy. So I told you this is kind of a sketchy topic, and it gets a little bit harder, especially when we get into energy conversions, because it's really, really hard to visualize that. I've said that about 4 or 5 times now. But basically this statement says that in an isolated system, if you were to take a system, let's say you play pool. Pool could be a system of objects. When you break that pool ball, you give that cue ball kinetic energy, and when it hits those balls, all of the kinetic energy of those balls would equal whatever the kinetic energy of the cue ball. All of that kinetic energy was converted into the other balls. You wouldn't gain energy, you wouldn't lose energy. If we were playing pool in an isolated system, we would even count the sound in there for the total energy. So this says the total energy of an isolated system remains constant. But let's talk about mechanical energy, because that's a little different. A conservative force, I used that term just a minute ago. The next statement says a conservative force is said to do work if an object, in moving it, the work done in moving an object is independent of the object's path. So a force is conservative if the work it does in moving an object is independent of the object's path. Well, the best example I can give you is gravity. If you throw a football, let's say you throw a football through the air. If the football is going this way, gravity's work is doing work in the downward direction. That force through that displacement on the football is downward. If you throw a football this way, work in the downward direction. If you throw a ball upward, gravity's doing work downward. If it falls back downward, obviously, you get the idea. So gravity is a conservative force. The work done by gravity is independent of the object's path. Gravity will always do work in the downward direction, regardless of the motion of an object, regardless of the motion of you, of a car, of any object that's here on Earth. Gravity is a conservative force. What about a non-conservative force? Oh, the next statement says exactly what I just said. So what is an example of a conservative force? Gravity is one. The work done by gravity depends only on the difference between the initial and final height and not the path between them. I like my explanation a lot better than that one. Similarly, a non-conservative force. A non-conservative force is said to be non-conservative if the work done by that force in moving the object or the work done on the object is dependent upon the path of an object. Can you think of a force that does work on an object that does depend on the path of the object? Let's think about that one. Just talked about it. Give you a hint. That's right, gravity. That's right, friction. Friction is a non-conservative force. If you're moving that way, friction depends on your path. It's opposite your motion or your direction. If you're moving that way, friction is that way. If you throw a ball upward, air resistance that is opposite the motion of the ball. So friction is a non-conservative force. So what does friction do? It often takes some of the mechanical energy of a system and diminishes it. So we already said that, if an object in motion wants to stay in motion, so if you roll a ball across the floor, if there were no friction, it would keep moving on and 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 on. The kinetic energy would be conserved. The kinetic energy would stay the same. But if you throw friction in there, now friction is removing some of that kinetic energy. It's taking away some of the kinetic energy of the system, and the ball slows down to a stop. Well, where does the kinetic energy go? If we said earlier that energy is conserved, where does the kinetic energy of that rolling ball, if it slows down to a stop, where does that energy go? It's got to go somewhere. You can't say that energy is neither created nor destroyed. If you lost kinetic energy, well, it went into the environment, maybe in the form of heat. The ball rolling across the floor, just like you rubbing your hands together really fast, produces heat. Actually, the ball would produce heat from friction for the floor. Now, could you measure that? Probably not in our laboratories at school, but there'd be some heat. How about sound? Could the ball produce a sound as it rolled across a surface? Absolutely. Heat and sound are produced by a non-conservative force, friction. It does not allow energy or mechanical energy to be conserved with that ball. So that's a great example of a non-conservative force acting on a system. I'm calling my rolling ball the system. When I say system, I mean any object or series of objects that we're talking about. It's kind of like a free body diagram. Free body diagram, you isolated a body and drew the forces acting on it. When you talk about energy, you talk about the term system. Well, a system is any object that you're talking about, the energy conversion is happening with, or it could be an engine. An engine would be a system of many moving objects where energy is converted. So I keep using the term system, but I forgot I really didn't define that for you. But the rolling ball loses kinetic energy because of a non-conservative force. I had a good example. I wish I would have brought some of those steel balls that you use on your lab where you predicted where it hit the floor. You can take those little steel balls, put some paper between them, and bang them together, and it'll actually produce heat on a piece of paper if you put it between them. You can see the piece of paper actually has some charred edges on it when you bang them together like that because of friction between the two balls. It's a pretty neat demonstration. I would have done that in class if we'd have been at school, and I'd have thought about it. I just thought about it right now. But so let's move on. I keep using the term mechanical energy, and oops, wrong slide. Let me think of that. Let me do this. Another way of describing a conservative force, it says if the work done by it in moving an object through a round trip is zero. Well, I always thought that was kind of a wordy definition, but it really makes sense if you think of it like this. We'll use my book as an example again. If I lifted the book off the ground, which way was gravity doing work on this book? So I lifted it upward, and of course gravity's force is downward. So gravity's force acts through that displacement. Which way was gravity doing work on this book? It was doing negative work. So we said the other day that was about 9.81 joules of potential energy that I stored in this. So gravity would have been doing 9.8 joules worth of work on this. Remember, work is force times displacement, and the force of gravity on this book would be its mass. We said it was 1 kilogram times gravity's acceleration, negative 9.81, and the distance that it moved through was 1. I'll write that down if you didn't catch that. So how much work was done by gravity? So how much work did gravity do? Work is force times displacement. So what force was gravity acting on that book with? Well, 1 kilogram times gravity's acceleration, that's the force due to gravity acting on the book, through, remember, force times displacement times 1 meter. So 1 times 9.1, we get 9.81 joules of work, but we said gravity's work was negative because the displacement was upward and gravity's force is in the negative direction. So gravity did negative 9.81 joules when I lifted the book. By the way, does that kind of look familiar also from a formula we talked about Friday? Mass times gravity times height. That's also the formula for gravitational potential energy. So if gravity did 9.81 joules of work on the book when I lifted it, then I must have had to have done 9.81 joules of work on it to lift it upward against gravity's work. So I stored 9.81 joules of potential energy in lifting it. So what happens when I drop the book? If I were to drop it from the same height, which way is gravity's work? It's in the negative direction. Displacement's in the negative direction. But that's actually positive work. So as I lower it, gravity does positive 9.81 joules as it goes down. So what's the sum of those two? Well, it's 0. Well, that's what this statement says. It says a force is conservative if the work done by the conservative force in a round trip, there is 0. So that's kind of a hard definition, but hopefully I explained it a lot better. The book doesn't really do a good job of explaining that, and this slide is really confusing if you don't understand what that round trip means. But that's the best example I can come up with. It's pretty simple. So, mechanical energy. Now we get finally to mechanical energy. I mentioned mechanical energy the other day. I gave you when we did kinetic and potential energy, I said that the kinetic energy, the elastic potential energy, and the gravitational potential energy was mechanical energy. So mechanical energy, often referred to as just E, so that's mechanical energy, is defined as kinetic energy plus all forms of potential energy. So kinetic energy plus all relevant forms of potential energy. Not all forms, I said all forms, but all relevant forms. Well, they only talked about 2 types of relevant forms: elastic potential energy and gravitational potential energy. So basically what you do is you take all the energy in that system and you add them boys up and see what you get. So if an object is moving along the ground, well, it only has kinetic energy because it's not at a height above the ground and it's not compressed onto a spring ready to be shot off or something to that extent. What about my bow example? If I pull a bow back and shoot an arrow. Let's say I shoot an arrow at an angle above the ground. Well, this system right here, actually has both types of potential energy. It has potential energy that I stored in the bow, but isn't the arrow actually above the ground also? So could you calculate the gravitational potential energy of the arrow as well? So the arrow, or the system, has stored potential energy, elastic potential energy, and the arrow has some gravitational potential energy both. So you have to see what the system of objects is defined as, and is it moving? Does it have kinetic energy? Well, my bow system did not have kinetic energy because it was not in motion yet, but it did have both types of potential energy, elastic and gravitational potential energy. So total mechanical energy is defined as the sum of all of that, the sum of kinetic and the two relative forms of potential energy if they're present. Some systems may only have kinetic, some systems may only have potential, some systems may have a combination of both. I'm trying to think of an example. A roller coaster, for example. A roller coaster, as it's going downhill, it has kinetic energy, but if it's above the ground, it has some potential energy too. And as it goes up another hill, it's gaining potential energy as it goes up the hill, as it increases in height, but it's slowing down because it's losing kinetic energy. So there you see some energy conversions going on, the conversion from kinetic to potential, and as it's going down a hill from potential to kinetic. So that's a good example of energy conversion. Probably the classic physics example of energy conversions is a roller coaster. So now you know what mechanical energy is. Let's talk about the mechanical energy of a system. It says for a conservative force, if only conservative forces are acting on that system, it says that the change in kinetic energy and plus the change in potential energy equals zero. It basically means this, that if you're losing potential energy, so that would be final minus initial potential energy, you'd have less in the end than you did in the beginning. That would be a negative number. Then it plus the change in kinetic energy, you'd have more kinetic energy finally, so that would be positive. So the sum of those two would be add up to zero. Basically that means if the change in both forms is zero, that simply means that you didn't lose or gain any energy in that system for a conservative force. So I keep using the term isolated system. Isolated system means that it's kind of imaginary, really, to be honest with you. It means that we're gonna take out all friction, we're gonna take out all non-conservative forces, and we're only gonna put conservative forces in this system. And if that's the case, then the change in kinetic energy plus the change in potential energy is zero. If you're gaining kinetic energy, if that's positive, then you've got to lose potential energy as a result. If you're losing kinetic energy, then you've got to gain potential energy as a result. And the difference in those has got to be zero. You can't get more energy out, or you can't lose more energy than you have put in. So that was kind of sketchy too. If we did some problems on that, it'd be really tough. But this is why I questioned whether to give you problems on conservation of energy, and I chose not to. My phone, email, remind would probably be blowing up if I gave you these problems on conservation of energy. So I just thought I'd explain conservation of energy because it is an extremely important topic. Basically everything that goes on in life is conservation of energy and energy conversions. For example, in biology, when you talked about the conversion of solar energy into chemical energy in the chloroplast of plant cells, that's an energy conversion. When you talked about cellular respiration, when we consume carbohydrates such as sugars and we convert that into mechanical energy, energy of motion in our muscles, that's an energy conversion. I've already mentioned car engines. Car engines take the chemical energy in gasoline, that molecule octane, and they convert that into mechanical energy, energy of motion in those pistons, and ultimately the drive shaft and the tires. That's that's conversion of energy. But even on a larger scale, the electricity in our homes is because of conversions of energy. It depends on the type of power plant. For example, a nuclear power plant would use the energy contained within the nuclei of an atom, and that's split in half and causes a chain reaction of other nuclei to split. But all of that energy contained within the nucleus is used to heat up water, and that water steam is used to drive a turbine, and that turbine is used to produce electricity. Same thing happens in hydroelectric. You have the kinetic energy of moving water, which is used to move a turbine, and that turbine in turn produces electromagnetic energy or electrical energy. Same thing in a windmill. If you go out west or in the Midwest, you look on a kind of a ridge, and they have all of these huge windmills. I guess I call them windmills. Look like windmills. That turn, and the blades turn, and that kinetic energy of the wind is used to produce electricity. Solar power, we take energy from the sun, and that energy from the sun is converted from solar cells is converted into electromagnetic energy. So basically everything, I always say everything in life is physics. Well, everything in life is also conversions of energy from one form to another. We may get all of the energy out of it if it's a conservative system. If there's only conservative forces, you throw non-conservative forces in there, we lose some of that energy to the environment. We don't, it's not gone, it's just converted into other forms that are non-conservative forms of energy due to non-conservative forces. Once again, I think I said this earlier, as a car engine heats up, when that octane in that car, we talked about this when we talked about friction, when that gasoline is burned inside of that engine, in those cylinders, it produces heat. Well, heat is not what helps your car go down the road. Heat is due to non-conservative forces. The mechanical energy from the octane is good. That helps your car go down the road. But the heat and the sound is a form of energy that's not used. So engines are about internal combustion engines are about 20% efficient at what they do. 80% of that energy in gasoline is lost to the environment, and so that's why energy conversions are so important. So this last slide on conservation of energy says, what if I'd say last, I skipped over a few slides, so I'm on one that says if a non-conservative forces are present. So what happens if a non-conservative force is present? Well, how do you figure that out? Well, you just take the amount of mechanical energy final minus the amount of mechanical energy initial. And once again, how do you find mechanical energy? You add up all the kinetic energy and all the potential energy. So the amount final minus the amount initial. And if it's anything other than zero, probably a negative number, because you ended up with less mechanical energy than you did. That tells you how much work was done by a non-conservative force. So basically, I'll say that again. Actually, I'll write it here. So you take all of the final mechanical energy, subtract all of the initial mechanical energy, and you get the change in mechanical energy. And once again, I said that's probably going to be a negative number, because you're going to end up with less mechanical energy than you did to start with if a non-conservative force is acting on the system, and that would equal the work done by a non-conservative force. So if you end up with, like, let's say negative 200 joules here, that means a non-conservative force did 200 joules of work on that system. You lost 200 joules of mechanical energy somewhere along the way. That could have been heat. Heat could have been produced as a form of non-mechanical. Sound, once again, light light could be non-conservative. So that's how you would find how much energy is lost due to a non-conservative force. All right, next video is power. I'm actually going to stop here because I know this video got kind of long and got kind of wordy, and you may have gotten confused somewhere along the way. I know what I'm trying to say. I know what I'm supposed to be telling you, but sometimes it might not come out that way. Good thing you don't have any problems to do over conservation of energy. But just know this, conservation of energy is what is basically important for life on Earth. You learned in biology that our ultimate source of energy is the sun for living objects here on Earth, or living organisms here on Earth. And if it weren't for plants and other autotrophs that convert the sunlight's energy into usable energy in the form of carbohydrates, glucose, and starches, then there wouldn't be life here on Earth as we know it. So that energy conversion alone is what maintains life here on Earth. You probably, if you took Mr. Kipp's AP Environmental Science, or if you Ms. Hawthorne's AP Environmental Science, you probably talk about the energy pyramid, that at the base of the pyramid are all your producers, your autotrophs, the ones that produce all of the energy for living organisms. But as you move up that, I guess it was the rule of 10 or something to that extent, that the next organism on there would be your primary, your herbivores, and your herbivores, they only get 10% of that usable energy from the plants. So where does the other 90% of energy go? Well, it goes into some other form that the plant uses. Plants grow, plants reproduce, plants do what plants do. And so they use 90% of that energy that they convert, and they only pass 10% on to the next level when they're consumed. Well, what about the next level? Your primary consumers that eat the herbivores. I think I'm saying that right. It's been a long time since I taught environmental science, but they only get 10% of that energy from the herbivores, those that eat the plants. So where did that 90% go? Well, let's say a cow. A cow uses 90% of that energy to be a cow, to walk around, to breathe. The heat that's produced during metabolism is lost somewhere to the environment. So that was that energy conversion process, that energy pyramid that you talked about in environmental science, especially AP Environmental Science. So there's a lot of interconnection here with your life sciences, or with just general life in general, like I said, with electricity. So I thought it was, I shouldn't think, I know it's important to cover conservation of energy. And as I said in the very beginning of here, it's pretty hard concept to understand. You can do problems over it, and yeah, they get kind of hard. If we were face-to-face in the classroom, I would have given you some problems, but I'm gonna save you the turmoil of having to do conservation of energy problems. So I'm gonna stop the video here, and I will be back on the next video, and we'll do power by itself. I will do a power problem, and I'm gonna need you to watch both of these videos today on Monday, so that you can do the problems on power. So check it out in just a second.